Okay, so in this video here, we're gonna take a look at exponential decay. All right, so it says, how long will it take 100 grams of radioactive substance having a half-life of 40 years to be reduced to 12 and a half grams? All right. Now here we are given actual values for my initial amount. Okay, and then how do I know it's decay? Well, half-life, right? That tells me that after 40 years, half of that is present. Okay, all right, so what we have here is the model is still the same, right? A of t is equal to A naught e to the kt. Okay. All right, and here it looks like t, we're going to have t to be in years, right? That seems to be the way to go about it here. And we're given our initial amount is 100, so we can even plug that in here. All right, and the half-life, right? Half-life of 40 years. So that means that A of 40 will have half of that 100, which is 50. Okay, but A of 40 is also equal to 100 e to the 40k. All right, and again, same as the growth function, right? We have these two values, and then we set them equal to each other. 50 equals to 100 e to the 40k. All right, and then from here, let's start solving for k, right? If we divide by 100 both sides, right, that simplifies it, reduces to 1. So e to the 40k. And then here, 50 over 100 is a half, which makes sense, right? Half-life. And now from here, let's take the ln of both sides. All right, so the ln that reduces here, and all we're left with is the coefficient 40k. And then here we got ln of 1/2. Sometimes our book takes this approach, which is a good approach, just kind of eliminates fractions here. 1/2 is the same as 2 to the negative 1, so you can just write this as negative ln of 2 equals to 40k. And divide by 40, so we get negative ln of 2 over 40 equals to k. All right, so now we've found our k, and plugging that back in, we have A of t is equal to 100 e to the negative ln of 2 over 40 times t. All right. Okay, and here, one thing that is different from the previous one, in the previous one they gave me how much do we have, how much is there after a certain amount of hours. Here we're kind of looking for the inverse of it, right? We're actually looking for the input, all right, where before we're looking for the output. So how much time, right, till it be reduced to 12 and a half. So when does that happen? So the way we do that is, okay, is equal to 12 and a half. All right, and then here, let's, same approach here, we divide by 100, so we get E negative T 40 ln of 2 equals to 12 and a half over 100 is 1/4, right? Okay, and then from here we take the ln of both sides. Sorry, not 1/4, 1/8. All right, so then from here, I take ln of both sides. And the ln reduces with this e, and all that's left is the exponent, so we get negative t over 40 ln of 2 is equal to negative ln of 8, right? Just taking that same approach where we can write this. This is the same as 8 to the negative 1, bring that negative out in front. And now here we just simply solve for t, right? So we're going to have plus, right, those negatives will cancel each other out, and we'll have t to be equal to 40 ln of 8 over ln of 2, right? Again, the approach I take here, this is in the numerator, so it's in the denominator on the other side of the equation. This is in the denominator, so it'll be in the numerator in the other side of the equation. Okay, all right, and then here I am done, well, almost done. We'll plug this into our calculator and see how many hours that is. Right, remember this is not the quotient rule, right? Since we have two different logs, so here we'll plug this in: 40 times ln of 8 divided by ln of 2, and we get 120 years. All right. 120 years to be reduced to 12.5 grams. Right? And that makes sense if we think about it, right? We can actually do this one, right, when it's a value that is 1/8 like that. So half of 50, half of 100 is 50, half of 50 is 25. So that's twice the half time, so that's 80 years. And then if we have it one more time, that is 12.5, which is, like we see here, 120 years. All right. Thank you.